universities around Indonesia. I believe lecturers, professors, also students from the universities will come to our WebEx seminar. Today's WebEx seminar is honored to host Professor Thomas Lei from Chang University, Taiwan. Before he starts his presentation on biological mechanical electromechanical system or BioMEMS for cell-based assay, let me introduce first shortly his curriculum vitae so that we can get to know more about Professor Lei's works. So, Professor Kin Fong Lei or Professor Thomas Lei is a professor in biomedical engineering at the Chang University, Taiwan. So prior to joining SGU, he was a lecturer at the Hong Kong Polytechnic University in Hong Kong. Then he received his BS degree from National Tsinghua University, Taiwan, and PhD degrees from the Chinese University of Hong Kong in Hong Kong in 2005, both in mechanical engineering. Then in 2006, he was a postdoctoral fellow at the University of Western Ontario, Canada. So Dr. Lei, at that time, has made significant original contribution in research in biomicrofluidics, in biosensing and molecular diagnostic. Overall, he has published more than 100 academic articles, also 8 book chapters. Professor Lei is a fellow of Royal Society of Chemistry, United Kingdom, also a senior member of IEEE, Institute of Electrical and Electronic Engineer, also member of American Society of Mechanical Engineer, ASME, and he has served also as chair for IEEE EMBS Technical Committee on Bionanotechnology and BioMEMS in 2020 this year, as well as associate editor at EMBS Conference Editorial Board in 2020. Also has served as a member of the organizing committee for several conferences, IEEE conferences on MEMS on microfluidic, IEEE NEMS in 2014 in Hawaii, and 2017 in Los Angeles, and 2018 in Singapore. He has also been associate editor for IEEE Access, as well as editorial board member for Scientific Reports Journal, Scientific Reports Journal, one of the member of the Nature Family Journal. So his main research interest is in MEMS and microfluidics or biosensing. Then he has many professional experience as researcher and scientist. Until from 2018, he has been professor in Chang University. Before that, visiting scholars in many several well-known universities in Germany, in US, in Hong Kong. Then I've mentioned his editorial services, including editorial board member in Micro and Nano System. Then he has been active in many research projects. I think that's all, but I think if we read his publication a lot, so I will just shorten the reading the CV. I think it introduces quite enough about Professor Lei, that he has been a active researcher and scientist in the field of BioMEMS and biomicrofluidics. For the purpose of this web seminar, would like to ask all the other participants to mute their microphone so that we can have clear sound. Would like to ask Pak Aulia to mute the other speaker, and then I would like to give the time and opportunity for Professor Lei to start his presentation on biological MEMS, and and also later a little bit introduction on Chang itself. So again, please for users, other users, please mute your microphone. How to mute is there is an icon, yeah, on the leftmost side, the microphone icon, which you can press to mute your
Jadi kita berlebaran. Boleh dikunjung-kunjung nggak sih? Tak boleh.
Oh yeah, you can possible to mute all the others. Yeah. Okay, Professor Thomas Lay, you can start your presentation, please. Thank you.
Yeah, thank you for your nice introduction. And first of all, thank you very much for inviting me for this presentation. And I have this chance to be here and at this specific occasion in such a occasion. And I'm very pleasure and very happy to be here. So I hope everyone stay well and hope that the virus will gone very soon. Okay, let me share my presentation. Okay. Okay. So I will use this presentation to give to introduce my research content. So the title is Biological Microelectromechanical Systems for Cell-Based Assays. So I'm from Chang University and I'm in biomedical engineering. Okay. So first of all, let me introduce the size and scale in our so-called Biomed system. Okay. So the scale is here is 100 micron. So I think you may, if you are not doing the micro scale research, you may not know how is micro scale. So let me have an example of what is micro scale. So you can touch your hair. So the dimension of the hair, the diameter of the hair is around 50 micron. So you have an idea of what is micron size. So in the nature, so the plant and animal cells is around 100 to 10 to 100 micron. Okay, for the bacteria, so it's around 1 to 10 micron. So it's around your hair is 50, so it's more or less around your dimension of your hair. So for the virus, it's around 50 to 100 nanometer. So this is why. So virus is much smaller than the bacteria and also the cells. And in nature, we have smaller molecules. For example, the protein, the DNA, is around several nanometer. So the smallest size of the in nature, so atoms, 0. something nanometer. This is quite small, and in nature, so in this is the what in nature in such a smaller cells. So in artificial world, so we fabricate some devices in this such a small length scale. For example, the insulator, gauge insulator, a transistor, or is around several nanometers. So in Taiwan, the TSMC can fabricate 4 nanometer transistor. I think you may know about this news. So for what we are talking about today is so-called MEMS. So it's around the 1 to 100 micrometer in size for a MEMS device. So I just want you to have an idea of the length scale. So today, the topic of today is so-called MEMS, Microelectromechanical System. So MEMS. So the length scale is around 1 micron to 1,000 micron. So it can be, it is actually in this area, this is pretty large. We can have a number of functions using the MEMS. So for the mechanical functions, electronic function, fluidics function, optics function. So nowadays, for the MEMS device, open a very large field for different functions. So today we are talking the biomedical functions. Okay. So, but I just want to have an introduction of what is MEMS first. So if we are talking about MEMS, this is the history of MEMS. So MEMS is from the semiconductor industry. So it's around 70 years ago, the first transistor, okay, invented by Biomed. And then the first IC from TI Texas Instrument is around 60 years ago, more 62 years ago, okay. And at that time, there's no MEMS device. And until 1977, so the first silicon electrostatic accelerometer was invented. So such that people think that in such a small scale, we can fabricate the electronic circuits and also the mechanical systems. So MEMS is so-called, from their names, there's some electronic system, electronic circuits, and also mechanical system, mechanical devices. So this is a combined system, right? Including the electronics and also mechanical devices. So in 1977, the first accelerometer has invented, and it realized a electronic circuit and also mechanical system on a silicon chip. So in 90s, in the last century, and a number of MEMS device was invented. For example, the digital mirror and also the optical switch. And nowadays we use a lot of accelerometer, for example, in your cell phone. So this structure is based on 1997. This is a commonly so-called analog devices. So they has the to push the accelerometer into large production. So at that time, and I think you know that at that time, the accelerometer becomes very cheap, and a number of applications can use the accelerometer. For example, the cell phone. So every cell phone embedded an accelerometer nowadays. So this accelerometer are based on the structure from 1997. So I just give you some example to show you what is the commercial MEMS product. So nowadays you can see, for example, the pressure sensor in the automotive industry. There's a lot of pressure sensor embedded in a car for measuring the tire pressure, right? And also the accelerometer to detect the acceleration and actually the airbag. This is so-called airbag sensor. It is an accelerometer. This is quite a number of applications in a car using the MEMS device. The second one, I think you all may know that this is the inkjet nozzle, the inkjet nozzle printer head. So it is to eject the ink from the printer head to the paper, right? It has some mechanical structure to push the ink, the liquid, from the ink tank to the paper. So it is embedded the electronic circuit and also the mechanical structure. Okay. This third one is the micro mirror. This micro mirror is kind of a mirror, but the mirror, the angle can be adjusted by the actuator. So in this illustration, you can see that there's a mirror and there's some structure to, this structure can use to actuate, to adjust the mirror reflecting angle. So this has some mechanical structure for sure, and also the electronic circuits on the silicon on the chip. The fourth one is the so-called RF switch for the communication applications. So this illustration shows you that the RF switch is just like a bridge, mechanical bridge. By the electrostatic force, the bridge can attach or detach to make contact or not in contact to the signaling line. This is for the RF radio frequency circuit, such that electronic switch may not work because of the high frequency. So they may need to use the mechanical switch to couple the RF signal to different directions. So this is also one of the example of MEMS device. Actually, MEMS device we use MEMS device, and nowadays a lot of MEMS device nowadays. So it is not a new product or technology, and everyone use this kind of the MEMS device. So I give this picture to you to show you how we integrate the electronic circuit and also the mechanical structure on single chip, single silicon chip. This is a accelerometer. This is from the analog devices. As I told you, analog devices is the first one to do the mass production for the accelerometer. So here we enlarge the image. This is a mechanical structure. Mechanical structure means the structure can be moved, right? So the gravity in this direction, the mechanical structure can move, and we can sense the gravity. Okay, so we embedded the mechanical structure and also the electronic circuit on single chip. That is so-called MEMS device. And I think each smartphone has this kind of the accelerometer. And MEMS technology moved the accelerometer to be small and also cheap. So everyone can use by this technology, everyone can use the accelerometer, very cheap. Okay. So today, the topic of today is not, this is the broad idea of what is MEMS, and we stream down and we are only talking about the biological applications, so-called BioMEMS, biological microelectromechanical systems, BioMEMS. Okay, this is one of the branches of MEMS. Right, as I told you, MEMS can be using the optical application, mechanical, electronics. Right, this is one branch of the MEMS. Let me define what is BioMEMS. BioMEMS, and also we call it microfluidics devices or systems, because most of the biomedical applications deal with water, deal with liquid. So we also call BioMEMS to be a microfluidic system or device. In a general definition, is this kind of the device or system is to handle and deal with small quantities of fluids. So this is a pretty broad definition of BioMEMS. Okay, so why we want to use microfluidics, right? So I list out some benefits of using microfluidic system. So it greatly decreases the reagent consumption and waste. So nowadays, if we want to do the blood diagnostic, right? So we sample the blood and then send to the laboratory for doing the analysis. So by using the microfluidics technology, we can miniaturize all this kind of the process into a single box. Okay, to make some benefits. So the first one, to decrease the reagent consumption and waste, right, and obtains the results in shorter time. So in the laboratory, normally we have the results around 2 or 3 days, maybe. However, if you have such a box, we can have the result in minutes. Okay, and because of this box, all the process are automation. So it has a better control process parameters, and enable the portable analysis. So actually, in such an occasion, I mean the COVID-19. So every country talking about the rapid diagnostic. So I think, as you know about that, some diagnostic take maybe several hours, one day. They still use the so-called PCR technology to do the to diagnose the virus from the sample. But some country use some kind of the rapid diagnostic to have the result in minutes. For example, in the US, they claim they have the result in 5 minutes, right? So in South Korea, they can have the result in 5 minutes also. So they build up some kind of the microfluidic system to do the diagnostic in such a small box, and such that we can have the result in very fast, and we do not have such a tedious process to process the sample and extract the RNA and do the PCR. A number of equipment to be used. So this is I think we can see the benefits of using the microfluidics at this, I think at this, especially at this occasion. Okay, so let me show you some commercial products of Biomed products. So this is also doing the diagnostic. This equipment is doing the so-called immunoassay to detect the protein. Okay, this is the machine, and this is a cartridge, such that they sample the blood from the fingertip, and then have the sample into the cartridge, and put the cartridge into the machine, such that the result can be the diagnostic result can be complete in minutes, several minutes. So before we have this kind of so-called immunoassay, it normally takes 6 hours or even more. But having this kind of the microfluidics device, we can have the result in very fast, several minutes. Okay, and I show you another one. This is from the Albert. Actually, this one is Albert brought this company here. Before it is here, however, the Albert actually brought this company also. Albert is a very large company in the US, and they have a number of the diagnostic equipment, the diagnostic kit. So this is also a handheld device, and they have sampled the blood and doing the electrochemical analysis to check to do the diagnostic for a number of proteins, and also the blood, the oxygen level, the iron level, for example. So it can have the result within minutes, 2 or 3 minutes, and it can be done all the process. So I just show you these two example and show you what is the application of doing the BioMEMS. And also the BioMEMS technology is pretty mature actually. Nowadays pretty mature. A number of commonly developed the rapid diagnostic kit, and we can have the result very fast. Okay, this is the benefits of the technology. Okay, this is the introduction of the BioMEMS, and then I want to introduce what I do in Chang University, and my laboratory is BioMEMS laboratory. Okay, my laboratory is doing the research related to cancer. So I use 2 slides to introduce you what is cancer. Okay, a cancer is a disease in which abnormal cells divide without control and can invade nearby tissues. So it is a disease. I think you may know that a cancer. This is a cell, but they have some mutation such that it proliferate abnormally. So from this cell, and they can proliferate a pretty large cancer tumor. So this is an illustration of a tumor cell, and the proliferation becomes abnormal such that this is so-called cancer. So I think what we study, what the researchers study cancer, I think the objective is only one objective, to do the treatment of cancer. We do not like cancer for sure. So all the research of cancer biology is doing the treatment for cancer, right? So whatever the chemotherapy, target cell drug, immunotherapy, gene therapy, Electro, right? So what we are, for sure, I'm an engineer. So what we can do for cancer, okay? So in our laboratory, so we are using the microfluidics technology. The application is the cancer. So what we are doing in our laboratory. So I just want to have let you have a pretty clear idea what we are doing in our laboratory. Okay, microfluidics plus cancer is what we are doing. The mission is to use microfluidics technology to accelerate the study of cancer. Okay, so today I give you 2 demonstrate or projects two area of our laboratory. The first one is to doing the impedance monitor of cellular responses. The second one is the so-called paper-based microfluidics. Okay, as I told you for the BioMEMS in the previous slide, the rapid diagnostic is pretty mature, right? The company can has already developed the rapid diagnostic equipment for all the immunoassay or gene analysis. So what our laboratory want to do? We do not want to do the rapid diagnostic because it is quite mature. You know, in the research, what is so-called research? So research means we want to do what everyone did not do. So we want to do using the microfluidics technology to do the cancer biology, to have more technology to accelerate the study of cancer. So this is what we are doing. So let's come to the first topics, the impedance monitoring of the cellular responses. So in the biological laboratory, in the general biological laboratory, in the medical school, I think you may know that this biological cell, they culture the biological cell using this kind of the plastic vessel. And the cell proliferate in the vessel and do the analysis. Or for the cancer, so we so-called cell migration assay. To have the cell, these are the cells, and has a scratch, and then the cell will migrate and to fill up the gap. So this is so-called migration, cell migration. These cancer cells can move to fill up the gap. Okay, this is quite a common assay in the biological lab. So the existing limitation of doing this kind of the analysis, they use the optical microscope to observe the cell, right? The cell only in the 2D observation because it is an optical microscope. And to count the cell, this is quite subjective. You count the cell one by one, okay? Or also they can use some kind of the bioassay to add some reagent to the culture well and do the assay using this kind of machine, okay? And however, this kind of the assay will sacrifice the cultured cell. They have to kill the cell before the analysis. And also, this is quite time-consuming and labor-intensive because you have to add the reagent to wait for a while and to do the reaction and then put the plate into this kind of machine to read the reading. However, it is good. It is objective. The analysis is objective, better than the optical microscope, right? The user can have to count the cell one by one. It is quite subjective. Okay, so there's some machine using the impedance quantification for quantify the cell, the number of cell, the cell variability. So they use the electro and the cell proliferate to grow on the electro by measuring the impedance across the electro. You can estimate the cell number. So it is real-time and non-invasive, and it is also objective. So this is an illustration to let you have a better, clear idea of what is impedance quantification of the cell. So there's the electro. Okay, so they have to connect the electro. Okay, and the cell, if the cell growth proliferate on the electro surface, such that the cell block the electro surface, and the impedance across this pair of the electro will increase. Right. So by the impedance, you can estimate the number of cells on the surface. So if the cell die, the cell will detach from the electro surface, such that the impedance will decrease. So by measuring the impedance, you can estimate the cell reliability. So this is quite a objective method approach to estimate the cell, whatever the proliferation or also the cell reliability. It is objective and also non-label. We do not need to label the cell. So, however, all these commercial products can only to measure the cell on the surface, so-called two-dimensional culture. So, however, in the nature or even ourselves, the cell live in three-dimensional environment. I think you may know that cell inhabit very three-dimensional environment in tissue. It is not the same as the cell living right just like that on a plane, on a surface. The biological cell do not live only on the surface in nature. They live in the three-dimensional environment. So those commercial products cannot measure the cell proliferation in the three-dimensional environment. So our laboratory target on this area, we want to measure the cell in three-dimensional environment. So in cancer research, we normally do so-called colony formation. So colony formation is to culture the cell in three-dimensional environment, such that the cancer cell will proliferate to be a colony, a cluster by cluster. So this is the early, so-called the early tumor. So in the biological laboratory, this three-dimensional culture is to investigate the development of the early tumor. However, in the biological laboratory, they cannot have no method, no technology to quantify the tumor. They still rely on the optical microscope to count the colony one by one. It is quite ridiculous I think for an engineer, it is quite ridiculous. We still use a operator to count the colony one by one. Okay, so we try to develop a impedance method to count the colony. So actually, it is quite simple. We use two electrodes to measure the volume of this, volume. Okay. So the cell culture in this volume, suspend in this volume, and growth just like that. The cell initially is individual cell, and it will grow, proliferate, and grow, becomes a one colony by colony. So we measure the impedance across this parallel plate electrode, and we found that when the colony grows, proliferate, the impedance will increase. So you see day 0 to day 7. Okay, the impedance increase day by day. Okay, so we can plot the index, so we call it colony index, to estimate the growth of the colony. Okay, so we try to have a drug testing to demonstrate this technology used by the drug testing. Okay, this is time 0, day 3, day 5, day 7. So this is the drug concentration, 10 microgram per ml, 50, 100. So from the image, you see that low concentration, the colony still can form. If we apply the drug in higher concentration from the image, right, the colony disappear. So this is quite a common and standard drug testing to test the drug, whether the drug affect the tumor cell. This is quite a standard project. However, in conventional, or even though nowadays they still use image to quantify the drug, the efficiency of the drug. It is not objective, right? So we use the impedance, as I told you. So this is, we form the colony 3 days before adding the drug, and at day 3 we add the drug by different concentration. Okay, control is we do not add the drug, so the colony still grow day by day. For the drug, so we can have the impedance. You can, from the impedance, you can have a quantity value to describe the drug efficiency. And then we can have the quantitative result for the drug concentration and also the cell readability. Okay, so right, if the drug is in low concentration, so all the cells still can grow. So this is so-called 100 readability. If we add very high concentration of the drug, all the cell kill. We kill all the cells, so 0% of the cell readability. So in between, we have different concentration of the drug. We can quantify with numbers to describe the drug efficiency. This is quite important for the pharmaceutical research to describe the drug efficiency. Okay, so we have this impedance. Actually, the idea is quite simple. However, we can use this technology to quantify the cell proliferation in three-dimensional area, three-dimensional environment. Okay, so this is the first one what we do, and the second one is we want to observe the cell moving, so-called cell cancer metastasis. Okay, if this is a primary cause of high mortality of cancer patients. Okay, the tumor will migrate from the primary cell, migrate to the blood vessel and to the distant site. This is so-called cancer metastasis. Oh, it is very dangerous. Okay, so many people in study what happened, why the tumor cell will grow, it will move, will migrate from the primary cell to the blood vessel in this area. Why? So-called invasion. Okay, this motion is so-called invasion. So we develop a system also using the impedance measurement to develop the system to quantify the interaction between the cell migration and also the extracellular stimulation. Okay, to have some numbers to describe the this phenomenon. Okay, so we developed this microfluidics chip. So it is two reservoir. Okay, let me show you here. So this is two reservoir and there's a microchannel. So in the microchannel we have 5 electrodes. Okay, just like that. The cell migrate from this reservoir through the microchannel to this reservoir. So when the cell moving, we measure the impedance by these 5 electrodes, such that we can monitor the cell migration speed. So, okay, actually this idea is also simple. We can demonstrate to describe the cell migration quantitative. So I show you the image. So the cell in this reservoir, these are the cells, can migrate from this end to another end. So 6 hours, the cell moving here, 12 and here, 18 here, and 24, and reach the destination. Okay, so with this 5 electrodes, we can measure the cell movement. Okay, this is time and this is the impedance. So we have 5 electrodes, E1 to E5. So the red one is E1. So the E1, the cell reach E1, the electrode E1 around 3 hours. The cell reach E2 around here, around 8 hours. E3, 15, okay, so and so forth. So because the distance of the electron, we know the distance, the time we can measure the time, so we can calculate the speed. Okay, right? This is the distance and this is the time. So we can have an average speed of the cell migration. So these are HeLa cell line and this is Hill7 cell line. So these two cell lines have different migration speed. So this is 0.20 millimeter per hour. This is 0.23 millimeter per hour. Okay, so we using this device, we can measure the migration speed very precisely. Okay, we have some stimulation to add some drug to the cell, and the migration speed will change. The cell migration speed will change. So, for example, for the HeLa cell, so without drug, the migration speed is around here. With 0.5 nanogram per mil, so we'll increase this migration speed, right? So such that we can have very precisely estimate to quantify the migration speed of the cell under extracellular stimulation. So this is the first one to demonstrate that we can measure the cell migration speed using a microfluidics device. Okay, in the previous two slides, we talked about some microfluidics device, which is using the so-called PDMS or glass discs. I think you may understand that most of the microfluidics device like that. Okay, however, we think that it is quite too complicated. Okay, is there any simpler method to do the 3D culture? Yeah, we try to use a paper. So aligned with the same idea, so we want to culture the cell in the three-dimensional environment and do the impedance measurement. So we use a filter paper to culture the cell. So as you see this illustration, okay, on the paper, we have some circular, we draw the circle on the paper, and then we apply the cell with the hydrogel, apply each circle, such that the cell can culture in this hydrogel, inside the hydrogel. And then we use a electroplenary electrode to measure the impedance of the hydrogel to estimate the cell viability. Okay, this is the illustration. So we have the plenary electrode. This is the paper. This paper is pretty thin, 200 microns, such that the cell in this hydrogel, we can measure the impedance across this electrode and to estimate the cell viability. So I just first I do a control experiment. Okay, so when we kill all the cells, the red color is dead cell, green color is the live cell. So we measure the impedance, so you can see if all the cells are alive, the impedance is quite high. If all the cells die, the impedance is pretty low. So we can measure the impedance to estimate the cell viability. So this is the image of doing different drug concentration. And so you see the Hill7 cell with doxorubicin drug. So if without drug, so all the cells are alive. So we apply 15 microgram per mil drug, so most of the cells die. So however, if we use the image it is very difficult to quantify the viability of the cell inside the hydrogel, in three-dimensional environment, using this image. So we use impedance, so we can have numbers to estimate the cell viability and calculate the drug efficiency. Okay. So I think you may know that in this project, you may know that cell can culture on a filter paper. Okay. So is there any and later on we found that we can have a more complicated application to doing the so-called cell biology. Okay. So in a cell, there's a number of protein in the cell. So we can, in general, we have to analyze the protein concentration in the cell. So however, in the conventional method, we have to do culture and doing the very tedious process to analyze the protein. This is quite a common process to do the protein analysis. However, if we think that if there is any easier, simpler method to do such a protein analysis. So we use a paper. So on the paper, again, we apply the cell on the paper and do the culture. So you see, this is the cell, this is the paper fiber. So the cell can live in the paper fiber. Okay, so we successfully culture the cell on the paper, and then we try to do the analysis. So I skip this. I just show you the results. Okay, so we analyze this protein. So when the cell number increase, the signal increase. Okay, that means we can measure the protein concentration in the cell. Okay, this is another protein. This is the negative control, right? That's when the cell number increase, the signal didn't increase. Okay. So for different kind of protein, this kind of protein, so we can analyze the protein in the cell, right? So then we demonstrated a example to analyze the extracellular stimulation and also the protein concentration in the cell. So when the stimulation increase, you see the signal increase also. That means we can analyze the cell signal using a filter paper. So we eliminate the tedious process, and we can analyze the protein signal using a filter paper, and within 2 hours. In the conventional method, at least 2 days to be have to use 2 days to do the protein analysis. However, if we develop this technology on the paper, we can analyze the protein within 2 hours. That is what we try to do to accelerate the study of cancer research. Okay, I just want to tell you these projects and show you two areas of our laboratory. So the first one is to do the imperimetric quantification of the cellular activity. So in both 2-dimensional and 3-dimensional environment. And the second topic is talking about the paper-based microfluidics. So we use the paper, the filter paper, to do the cell culture, to culture the cell on the paper, and also to do the protein analysis. This provides a fast and convenient tools for the first-tier screening of cancer signaling pathway. So we can analyze the protein on the paper. Okay. So finally, I just want to do some acknowledgement. So in Taiwan, we have a Ministry of Science and Technology, and I really appreciate for the financial support from them, and also our hospital, Chang Memorial Hospital, and they provide us a number of funding to support our laboratory. So I also appreciate to my students and also my research assistant and also my lovely doctor, these two. So to support us for this laboratory. Okay, thank you very much for your attention, and I hope that you have an idea of what our laboratory do, and to share with you our recent development in our laboratory. And if you have more questions, actually you can go to our laboratory website or email to me. It is okay, and to see what we have done in the previous day. Okay, this is the technical content, and I hope I'm not speaking too fast and too rushed for this. Because it is quite a special experience for me to talk before the screen. This is quite strange for me without audience. So I may speak too fast. I hope you can understand. Okay, and then the next part is I just want to have some slides to share with you our university. Okay, this is our university, is Chang University. This is our campus. So actually, our university is not that huge, and I can say it is small. we only have 3 colleges. One is medicine. Actually, our university start from the medicine. Okay, we are in engineering, and the third college is management. Only we have 3 colleges. So the total number of students is 7,000. It is not a big unit. I can say it is a small university. Okay, we only have 7,000 students. We are a private university. It's founded by Formosa Plastic Group. Okay, we are here, so China, and we are here. Okay, I think we are not too far from Indonesia, right? 4 to 5 hours, I believe. And again, we founded by Formosa Plastic Group in 1987. Oh, it's only 30 years for a university. I think 30 years is not a long history. It's a quite young university, I can say. So Formosa Plastic Group is a very huge group in Taiwan. It has a 50% Taiwan GMP, and so we are the biggest group in Taiwan, and this group has a number of companies for refining plastics, semiconductor, machinery, power plants, transportation, biotechnology, hospital, education, etc. So every area, the Formosa Plastic Group has their company there. So we are one of very small unit under this Formosa Plastic Group. So we are university, and actually we also under this Formosa Plastic Group, we have a huge hospital system. Okay, if you remember, university is only 30 years old. However, the hospital is 40 years older than university actually. So they think that they establish the hospital system, and then they want to have their doctor, such that they establish the university 10 years later. Okay, so nowadays we have a number of hospitals in Taiwan, Taipei, so Linkou, Keelung, Kaohsiung, Jiayi, Taoyuan, Yunlin. So quite a number. We have 17 hospitals in Taiwan and also mainland China. We have hospital in Xiamen and also Beijing. So we are actually it is the largest hospital system in the world. We have over 10,000 beds in this hospital system. Okay, so and also in the university has a very close relationship with the hospital. So we have a number of very close funding system, and also the collaboration, and the doctor in the hospital are also the professor in our university, and we have very close relationship, and we can have the sample from the hospital for sure very easily. And actually, we are under the same Formosa Plastic Group, so we are very close together. So let me introduce our college. We are in engineering college. We provide master program and also the PhD program. So I am in biomedical engineering. I think you are in the electrical engineer. So I highlight this 4 in red. I think it's more close to you. So we are in biomedical engineering, and we also have electronic engineering. And there's a very special program I will introduce to you later on. And actually, I'm the program director in this program. We have PhD program. Also, we have the BME and chemical engineering, computer science, electrical engineering, electronic engineering, and also mechanical engineering. So I guess these 3 are more close to you. So I highlight in red. So Chang University also promoting the international student, and we hope we can have more international students in the future. So I hope in the future we can have more collaboration, whatever, you can have some exchange arrangement, or your student can join us. So the application period for the fall admission is just past April 17th until April 17th, and the spring admission start in September to October for the spring admission. So in our university, all students can stay in the dormitory on campus. So you don't need to worry about the living. So it's quite, I believe it is not pretty expensive. 4 students can live in the same room for this price, a 4-person room. Okay, everyone can stay in the campus. The tuition fee is NT Taiwan dollar, around 75,000 per semester. So each year we have 2 semesters. Okay, and we provide a number of financial assistance, the scholarship, the full tuition waiver. So it is competitive base. When you apply our program, we will evaluate your application and give you the scholarship. So after the acceptance, you can decide whether you can come, have the full tuition waiver or no. So we will tell you when you are in the application period. Okay, and also we have a number of TA, teaching assistant or research assistant opportunity. It depends on the supervisor. Some supervisor, for example, for a PhD student, they can give pretty high, up to 24,000. For the master student, maybe 6,000, 10,000, depends on the supervisor. You have to talk with the supervisor. However, I can say that in Chang University, every advisor is pretty rich. They have a number of funding to support the student. I believe each student can receive enough financial support from the supervisor. Okay, and lastly, I want to introduce this program. I'm the program chair, program director of this program, so that I just want to promote our program. This is a master program. Okay, so this is a joint program with Singapore University of Technology and Design, SUTD. Okay, this is a dual master program. So if you join this program, you will have 2 master certificate. Okay, the first 9 months is in Chang University from September to May. We do not have spring admission, only 4 semesters. So in September to May, next year May, so in Chang University, and then in June, early June, student will go to Singapore SUTD for another 6 months. So it is a package. So 9 plus 9, 18-month program. So you can have 2 master certificate. One is from Chang University, Taiwan, and another one is SUTD Singapore. So we only have 4 admissions. Okay, because this is a batch and batch student, aligned with the timetable of. So the 4 admission is June to April. The tuition fee is higher than the regular program, 75,000 per semester. For sure, we also provide scholarship, full tuition waiver, plus 8,000 a month. So we give 18 months. Also, it is a competitive base. So when you apply this program, we will select the best student to have the scholarship. When you arrive, you are pretty sure to have this scholarship. But there is some criteria. If you fail in a number of classes, we can stop your scholarship. But we will tell you in advance. such that you can prepare your financial arrangement. You can prepare before coming to Taiwan. Okay. Okay. That's the end of my presentation, and I hope you can enjoy the talk. And if you have any question, please ask me.
Okay. Thank you very much, Professor Lei, for the very interesting, nice presentation on BioMEMS for cell-based assay, and also regarding the Chang University and the program, the master program also. We already have several questions, which is given to us through the chat box, also from the YouTube live. So we have actually about 40 participants in this WebEx seminar, and from YouTube we have 25 viewers in attendance. So I will give you one question first. First question this is from our lecturer at SGU, Mr. Eka Budiarto. He has a question about microfluidics. His question is, what is the connection between the small size fluid to the speed of the analysis? Because you were mentioning that by doing the analysis, the assay in microfluidics, then it is faster compared to when we are doing the analysis in large-scale machine. Then, is the analysis always faster if the amount of the fluid or sample very small? I think, yeah, you may answer first that question, but then if you have answered, we have another question actually waiting.
Okay. So this question, for example, in this machine, okay, all the reagent pre-installed in the cartridge, such that the blood sample putting into this reservoir, all the process will be automatically performed in the machine, such that your question is, all the analysis will it be faster compared to the conventional assay? Yes, because in the conventional assay we have to do the mixing, to do the reaction by human body, by operators, right? So we have to transfer the reagent from one vessel to another vessel. So this takes a lot of time, and we need to have a number of equipment to conduct these experiments. So for using the microfluidics technology, we can make it automatically, and we have a very small size in the vessel. It can enhance the surface to volume ratio, such so-called surface to volume ratio. So the protein can react with the protein reaction will react on the surface, right? So the volume, if the volume very small, and such that the protein in the volume can be easily to react with the protein on the wall, on the vessel, it can enhance the accelerate the analysis time. So that is my answer.
Okay, thank you. So, yeah, we understand. So maybe we go then to the second question. I hope the answer from Professor Lei answers Eka's question. Okay, Professor Lei, there is a second question here regarding the cancer diagnostic. This is from our graduates, from our alumni, Ms. Fatia Nabila. She has questions. How can we use the technology, especially the microfluidics, to do diagnostic or monitoring at the molecular level? Her question is because, for example, with cancer, as you have presented also the case with cancer, cancer deals with genetic mutations. And for some cancers, the treatment monitoring is done at molecular level. She gives example, for example, the treatment monitoring for lung cancer is usually done by monitoring if the EGFR gene mutation is still present or not. So how can the monitoring at this molecular level, at the for example, the genetic expression, can be done using your approach in BioMEMS assay?
Yeah, thank you for the questions. I think in the conventional laboratory, we analyze the protein, the molecular level, the protein using the so-called Western blotting assay. So we have the cell culture and extract the protein and doing the Western blotting assay. So this is a really tedious process to analyze the protein. By using our approach, we culture the cell on the paper and then doing the stimulation, and we can have the protein analysis on the paper, okay, to do the primary antibody, secondary antibody analysis, and do the amplification of the signal. We can perform this tedious process on a single paper. So in the conventional one, we have to transfer the protein for the protein from here to here and to do the electrophoresis, the transfer, and to do the signal amplification and to signal capture. Such a tedious process. We can combine all this process on a paper. So it can, we can accelerate the study of the protein, the molecular mutation. So we are not doing the cancer research, but we have to accelerate the study of cancer. That is, at the end, we are the engineer, so we do not know what is the mechanism of the cancer. However, we can invent some tools to accelerate the research of cancer. This is what we are doing.
So in short, that the mechanism is done within a single platform rather than having to transfer from machine to machine. That will be the main benefit, right, of your approach.
Yes. And also shorter the time. We only have it takes 2 hours. However, for the conventional one, it takes always take 2 days.
But then can the changes of the gene expression, for example, the participant was asking whether to detect a single gene expression in this.
Yeah, the single, for example, in this slide, this is the one of the protein. So it is step 3. So by the stimulation, we can detect the single protein expression, okay, the level of the changing of the protein using our approach. We still can detect the difference.
Have you ever tried with genetic expression aside from protein expression? Well, looking at the gene expression level or the DNA expression level, for example?
Yeah, the colorimetric signal represent the activation level of this protein. Okay. Yeah.
Okay. Yeah. So then we can maybe proceed to the next question by another student of our university, Professor Miss Elgas. She asked these questions for the protein analysis, because we mentioned also about P-STAT3. She was looking, how do you know about the selectivity of the analysis? Because according to her, you are measuring some proteins in the cell. How do you know that your diagnostic, your assay for that particular protein is selective, that you are not seeing the expression of other protein, for example?
Pardon me?
The selectivity issue in detecting particular protein expression or activation in the cell.
I can show you in this slide. So this protein is GAPDH. I think if you are in biological science, you know that this is a housekeeping gene. This is the actin. This is quite a large number in the cell. So one cell is a huge number of this kind of the proteins. So it can detect the housekeeping gene, increase the signal with the number of cells. I think it is quite easier to detect. So you said the selectivity. So this protein is so-called functional protein. The cell do not have large number of this kind of protein, up 1, 2. However, we still can detect the signal with increase of the cell number. However, the sensitivity may not as good as the housekeeping gene. So you can see, right, the increasing where the number, the signal increase with the when the cell number is in low concentration. However, for this protein, the functional protein, the cell number is significant large number of the cell number. We can still detect the signal. For the specificity, so it depends on the primary antibody. It is not depends on our system. So I think the sensitivity, just show you the sensitivity. We still can detect the functional protein and also structural protein. The specificity depends on the primary antibody that our system cannot control the specificity.
Thank you, Prof. Yes, I think very clear answer to Ms. Elga's question. So the selectivity is determined by the antibody used for conducting the immunoassay of the cell signaling. Not on the platform itself, but on the antibody being used. Okay. We have next question from Ms. Larasati Tanjung. This is our guest from the Faculty of Veterinary Medicine in IPB, Bogor Agricultural University. Yes, question about the survival rate of the cancer cells on the paper-based device compared to the survival rate of the cancer cell on the usual cell culture, on the usual PET cell culture. Is it harder for the cell to survive on paper rather than on the cell culture? And by that way, would this affect the measurement in the device? That is her question, Prof. So comparison between the cell survivability, cell culture survivability in the cellulose-based platform and in the PET-based platform, in the conventional plastic cell culture. How do you compare that?
Yeah, what we observed that because why we want to culture the cell on the paper, because we want to do the assay. Whatever the protein, right, or the protein or the cellular interaction. So the culture, we try to culture the cell up to 5 days. It is no problem. The cell can culture on the paper for 5 days. So most of the assay within 5 days. So we think that our system can deal with most of the assay. So for the plastic plate, you can say for the plastic plates, the conventional plastic plate can be cultured up to weeks. However, our approach is to do the assay. So we are not to do the cell amplification. So we do not culture the cell over 1 week because 5 days, 1 week should deal with most of the assay. So we think it is enough for most of the assay. So we did not try to culture the cell for months. No.
Yeah. Okay. I think that is quite clear enough. I think because the necessity for the assay are only for several days, right, Prof? So we do not really need very long survivability of the cancer cell on the platform.
Yeah.
Okay. Thank you, Professor Lei, for the question, for the answer. We have another question from the YouTube. from our lecturer, Mr. Maulwi Panjaitan. Is it possible that we use this technology, yeah, maybe the microfluidic or also maybe the paper-based microfluidic, for the detection of the COVID-19 disease, yeah, the SARS-CoV-2 virus infection? Then his second question is using your platform for cervical cancer diagnostic. How is it possible? Is it possible to use this also technology for cervical cancer diagnostic? Yeah. Two questions. So the first one is on COVID-19 diagnostic. Second one is on cervical cancer diagnostic using the microfluidic platform.
These two questions is about the diagnostic. The first question is that okay for the COVID-19? Yes. However, for the sensitivity of the paper-based or the paper-based diagnostic is not that sensitive. For example, for the we are calling the lateral flow assay. For the conventional lateral the pilot test, you have a test strip to do the pregnancy test. This is also one of the microfluidics. However, the sensitivity may not be that good. I think you may know that. So the molecular diagnostic return to the conventional diagnostic. So for example, the PCR for the gene diagnostic, PCR diagnostic, or the immunoassay using the 96 culture plate to do the immunoassay protein assay return to here. However, for these two conventional assay, for this machine, it is also the immunoassay. So they detect the protein. However, they ought to make this kind of the process into the cartridge. However, the core is also the immunoassay. However, it can be very fast. So you have to trade off. You want to have this higher sensitivity. So you may use this kind of the conventional technology. However, to miniaturize this kind of the technology in a machine to accelerate the diagnostic. For example, there's another machine to do the PCR. This is very fast. I think I saw the video for the COVID-19. They use the this video made the machine. Let me show you. Maybe let me show you the. Because I stopped this sharing, and then so I think you may saw in the video for this machine, the Gene Expert system. They are doing the COVID-19. They are not like the conventional PCR machine with the cartridge, and they can accelerate the diagnostic time. So we balance between what is so-called microfluidic. So I just in the beginning of this presentation, I just give you when a system deal with small quantity of fluid, we call it microfluidics. Whatever that look like. Okay. So so the second question is
cervical cancer.
So we always again if we're doing the diagnostic for the cancer, we always to diagnose to detect the protein. So it returns to the immunoassay. Okay. Yeah, so we have some biomarker for the cancer. So we have the blood, we have the patient blood and do the analysis of the protein. Oh, so actually in our research field, we have most of the microfluidic guy deal with the diagnostic part. Whatever the protein or the gene diagnostic, molecular diagnostic. So I am another group of the microfluidic guy. I do not do the molecular diagnostic. Actually, I do with the cell biology.
Yeah.
So because what I think is the rapid diagnostic is quite mature. So in the university level, we have difficult to compete with the company. Right? They are great big company that is we cannot compete with them. So we move to another cutting edge area to do the cell biology using the microfluidics technology. Yeah, this is what I think. Yeah.
Okay. Yes, I think I understand and I agree with you that we cannot compete with big technology. Yeah, especially to compete within the same aspect. Yeah, PCR, for example, they are developing it quite enormously, intensively. So we have to use, in order to compete, we have different kind of approach, so that we can stay in the cutting edge. Thank you, Professor Lai, for that insight. Are there any questions from the audience? Yes, we have from the YouTube channel from Miss Siska Alicia. Yeah, so her conclusion is that your technology that being developed is mostly for protein level detection using antibody, so not yet for messenger RNA or DNA level detection. Is it correct that if you conclude like that from your presentation?
Actually, I learned from the biologists. For the biologists, there's two groups. Some biologists always want to detect the gene. Another group is always want to detect the protein. Right. So I prefer to detect the protein because the protein is the output of the cellular response.
Okay.
Yeah. So I do the protein more than the gene, but some projects we do the gene analysis because when the cell the number of cells we collect the cell in a really small number. For example, we can only collect 100 cells. We may do the gene analysis because we can do the amplification.
Okay.
Right. So sometimes we do the gene analysis, but most of the time we still trust the protein because it is the output of the cellular response.
I see. Yeah. So most of the time you do the protein expression on the, because that's at the cellular level, but it is possible. Actually, it is possible for conducting also molecular level diagnostic or assay, but maybe in your group case it is not often done. Is it like?
Yeah.
Thank you, Professor Lei. Are there any other questions from the audience? We are seeing not yet any other questions. Audience may also ask regarding Chang University, maybe in general, or regarding the master degree program that Professor Lei is conducting with the Singapore University of Technology and Design. Yeah, so far no questions, Prof. Lei, from the audience. I think, yeah, maybe your presentation, I think, is very clear. You have presented as well the references, which maybe later we can also look into, yeah, to the references that pick up your presentation. So I think if there is no other questions from the audiences, yeah, that will be all. Actually, we still have about 10 minutes time, but I think it's okay also if we can finish earlier. We are very gratitude again. We are very thankful to you, Professor Lei, for giving this opportunity and time to share your experience and research to us here in Indonesia, especially to our universities, Swiss German University. And we do hope that we will have future fruitful, long collaboration between our universities. And we are also welcome to the guests from other universities and institutions in Indonesia. If you would like to do collaboration as well with Chang University, but also good if also with us together with from Swiss German University and then multiple parties and multiple universities, I think that will be also good. Again, thank you again to Professor Larry for the presentation. Thank you all for to the guests from our university SGU, as well as from there is one question. Yes, from one small question, Prof. Larry, before I conclude. This is from Mr. Gunado Hassan from University Sumatera Utara, from other island in our country. Yes, Mr. Gunado Hassan, please throw your question. Yeah. Let's wait for a while, Professor Lay. Yeah. Okay, his question is regarding the application of BioMEMS in diagnostic, cell biology and therapy. Well, actually, you already give your some in many of your answer to the other question, but perhaps you can summarize a little bit more for our guest here, Mr. Hassan Bonado. In general, the application of BioMEMS for diagnostic and cell biology and therapy, maybe in summary, Professor Lay.
Yeah, most of the researcher in microfluidics or BioMEMS doing the rapid diagnostic. So in this occasion, the COVID-19, so some country do the diagnostic very fast, but some do very slow for days, actually. But I think you heard that although they did not tell what technology they have, however, in the US or South Korea, they can do the diagnostic with 5 minutes. So I guess they adopt the microfluidics technology to do such a fast diagnostic. This is the conventional microfluidics guide to do. Nowadays, the academic move to do the to observe the cell biology in the microfluidics device, because the cell response may not have the in such a large conventional vessel cannot have precisely express their response. So some researcher may build up some microfluidics technology to do a more precise monitoring of the cellular response. That is two group for the microfluidics guy to do. Actually, I think you may agree with that. The technology moving so fast, so some researcher doing more advanced research in microfluidics. But now the goal of the microfluidics is to do the applications, just like the semiconductor. So so we use the semiconductor to do your applications, not really to do the research of the semiconductor. So I think again we also the same. The microfluidic technology is quite mature, so the researcher want to find the application using the microfluidics technology. So I think the technology is moving, and we are changing day by day, year by year. Yeah.
Thank you, Professor Lay. I think that it is quite clear answer for the question. Maybe one last question here from our guest from Telkom University, Mr. Estananto. His question is regarding the material used for the 3-dimensional cancer cell detection in your presentation. I believe it is PDMS, or maybe you have other question, other materials there. His question is, what material is being used for the 3-dimensional cancer cell diagnostic in your presentation?
We encapsulate this cancer cell in the hydrogel.
Okay.
So the cell, suspend in the hydrogel.
Yeah. The hydrogel itself is from the cell culture medium. Is it like that?
Yes. For the artificial hydrogel, for example, the aqueous hydrogel, the mesocellus hydrogel, right?
Yeah. Okay. Thank you. Then maybe one more question here. I think it will be the last question, but maybe you can answer shortly. Is it possible? This is from our guest from Bogor Agricultural University. Is it possible in the near future to have device which allows us to decide whether a sample is cancerous or not? Yeah, a tissue sample maybe is cancerous or not. Since usually for cancer diagnostic they are to confirm, usually it is done by biopsy, tissue biopsy. Then is it possible to do the diagnostic whether the tissue is cancerous or not without cell amplification procedures? So usually the in the histopathological lab they will culture the tissue again to grow it or to make the cells proliferate, and after that only that they can do the diagnostic whether it is cancerous or not. But his question is it possible we don't need to do cell amplification so that the diagnosis can be done faster?
Normally, we use the blood for the cancer diagnostic to diagnose the protein in the blood. This is quite a common way to do the cancer diagnostic. I think if you want to diagnose the tissue, it is very difficult to collect the samples. Actually, we have some collaborator in the hospital. The physician told us that nowadays they eliminate to collect sample from the tumor because there is so-called invasive operation. So patient may have some damage. So the physician seldom to take the tissue from the tumor. But we move to do the blood diagnostic, so-called the circulating tumor cell, to isolate the cancer cell in the blood. So because this kind of the cancer cell is migrate from the tumor to the blood vessel, so we collect the blood sample and to do the circulating tumor cell to isolate them and to culture this kind of so-called CTC, circulating tumor cell, into in the conventional dish, and to grow up and to analyze this kind of the CTC to diagnose the gene, to diagnose the gene actually for the target cancer treatment, to decide the target. Yeah.
So Mr. or Miss Dinda, I hope the answer from Professor Lei is quite clear. So normally now biopsy is quite invasive, so the approach is to use circulating tumor cell from that is available in the blood sample, and then culture it and then do the diagnosis, the cancer analysis. Okay, I think I would like to conclude. That's all because it's already 2:30. Thank you very much, Professor Lei, for the opportunity and time for us, and thank you all the guests from SGU as well as from other university institutions for attending this WebEx seminar. I would like to return back to Mr. Aulia Iskandar, our host, the session.